Sure. So good afternoon, everyone. My name is Manoj. I welcome you all for this seminar session. So from TriboNet, we are organizing this seminar session on various topics related to tribology and lubrication. So we are inviting the guests from various industries and universities. Today we have with us Professor Andreas Almqvist, who will be talking about the topic reducing friction in skiing. So I will be giving a brief introduction about him. So Professor is working currently at Luleå University of Technology, Sweden, in the Department of Engineering, Sciences and Mathematics. He is the scientific leader for the 4-year computational tribology project, which is focused on multi-scale topological optimization for lower friction, less wear and leakage. He's also editor-in-chief for the Proceedings of the Institution of Mechanical Engineers, Part J, which is the Journal of Engineering Tribology. He has also recently won the award for the Swedish Olympic Committee Research Fellow. So, Professor, we are so delighted to have you here and for this talk. I hope you're happy as well.
Thank you very much for the presentation, Mano. Yes, that's the role that I'm most proud of, I must say, at the moment, to have been selected by the Swedish Olympic Committee as a research fellow there. So it feels really nice. Of course, I love my task to be the editor of Journal of Engineering Tribology. So I guess the title of this talk was distributed to be something like ski friction or so, and it will definitely involve ski friction, but you can see this more as a report of what we are doing in the ski and snow lab here at the Luleå University of Technology. And let's see now. I tried to change slide. Okay, I must change slide this way. So the outline of my presentation looks like this. I will start with talking about performance and how that is connected to this friction, of course. And then I'm going to describe what's going on in the ski and snow lab about ski technology. And of course, we will dwell into the frictional behavior of cross-country skis on snow. And we will focus on, here at the Ski and Snow Lab, we focus on the friction among the resistive forces there are. Of course, we have aerodynamic drag, which may be very large player here. And we can also have gravity if we are going uphill to cause quite great resistance. And then, well, when we look at that friction, we must, of course, consider important factors that affects the glide, affects the friction. And then I will show you how we can quantify this and what tools we have, what methodologies that we have and we use to quantify friction. And in the end, I hope to deliver what we aim at, namely to optimize the performance for an individual athlete. So if you look at this performance loop, you realize that it is about how the athlete's physiology and biomechanics and the sport specific technique and technology together contribute and collaborate in producing propulsive forces and in causing resistive forces. So resistive forces that we have been focusing on here in Luleå. And the ski tech team here in Luleå, we work together with the Swedish Olympic Committee and the national teams in both cross-country skiing and in biathlon. And what we are trying to do is to carry out real scientific studies on how to select ski type, ski base grind, the waxing and metal embossment drilling to optimize the glide performance for different conditions. And we work currently in 3 parallel but highly interconnected tracks. So we look at both the interaction between the biomechanics, the skier's biomechanics, and the material. And then we have a sort of a virtual ski laboratory where we build models based on what we have already from machinery tribology and continuum mechanics in general. And then we build and then develop tribometers and test methodology to actually quantify friction in skiing. And we are quite few that are engaged in this project here at LTU. And 2022 the teams looks like this. So we have 6 people to the right, 3 up and 3 down. We are at the Tribology group here in Luleå. Perhaps you recognize Roland Larsson, who is the head of the division, and Nasani Nemami, who is very good in both biotribology and polymer tribology. And then we have 3 PhD students I have listed here, and we have a 4th incoming. You will perhaps hear, well, let's see. They are, of course, working in these projects very intensively at the moment. They have just come back from a visit to Italy, where they have been, taking a course. They have been visiting university who is very good at biomechanics. And they have also visited the 2026 Olympic Stadium, both for cross country and for biathlon. So, and in the middle here, the 4 in the middle, they are the people from Swedish Olympic Committee and coaches and other that connects us to the national teams. And the 4 to the right, they are belonging to the experimental mechanics group here, and they are doing the snow science, one can say. So they are researching into the snow mechanics, for example. Now, with that said, we all know friction is a system property, and it is dictated by the material and the properties of the surfaces in contact. But it's also important to remember that the prevalent conditions contribute to the resistive forces that develops. And here I have 3 different conditions, 1, X, and 2. And I think most people who have some kind of own experience in skiing can answer question A, which says in which of these cases the friction is the lowest. I guess so, at least by these schematics. Perhaps these images are confusing you somehow. But perhaps not all of you can, and hopefully after this webinar you can. You will be able to answer it. But what we are trying to do is, of course, we are trying to answer why this is the case. And to do that, we need to consider a number of different factors. For example, the load, the skier's body weight under gravity and on the track in all directions will, of course, affect the friction. The frictional behavior, I should say. Geometry of the ski and of the track itself. And then on the micro scale, the surface topography and the snow. What is the snow surface looking like at a certain condition? The hardness of the ski base and the hardness of the snow. And here I've listed an acronym which is the base material in skis. So we have ultra high molecular weight polyethylene. And that can be, of course, doped with different other constituents to enhance the gliding properties and, well, the wear properties also of the material. Wetting, we know that hydrophobicity is a player in skiing. So both the wetting and the surface tension. Sorry, I get these pop-up messages right in the middle of the screen. People are needed to be admitted to the talk. Anyway, shear resistance of the melt film. So if we have any water developing in the contact, that we need to shear that, and the viscous friction is causing resistive forces. Perhaps we can have some kind of hydrodynamic lubrication there, but I don't think it's beneficial. Contamination, and here I have a Swedish word, smuts. It's dirt. But particles, energy drink gel is horrendous to get beneath your ski if you want to have good glide properties. So avoid that. Organic material. In the springtime, we have leaves and we have bark and these needles, pine needles coming down from the trees. And when you glide over them, you will smear that in and create a tribofilm which is detrimental for the glide. So then, okay, if these are maybe there are other factors too, but these are quite main players. So when we know them, we also need to be able to quantify, to analyze and quantify the effect of them. And for load, for example, we can do plantar pressure measurements. So we put an insole in the skier's boot, and we can measure the plantar pressure distribution. So we know how they position, how their position affects the equivalent loading position on the ski. We can also measure the pole force with specially equipped poles, skiing poles. And by this we can tell quite a lot about the resistive forces during skiing, actually, for a athlete performing skiing in various techniques. For the geometry, we can use ski camber analysis devices, machines. One example is a giant profilometer stylus that just measures the height of the ski when it's subjected to a certain load. We can complement that by numerical methods to tell more. Same thing with ski mechanics, can also be estimated or analyzed with ski camber analysis methods, and we can do also numerical complements to this to understand better, of course, how the ski behaves when we subject it to racing conditions. Surface topography, the usual tribological equipment, profilometry, optical today typically, and microscopy, of course, and others also like 3D computer tomography. We can also have. I will show you some example of this. And then, of course, we need to measure the composition, hardness, wetting of the material and wax, and also the viscoelasticity of the material is an important factor. Now, skiing means that we are, or friction in skiing means that we are viewing a multi-scale and multi-physics problem, like most of the tribological systems that we have. They are mostly of this type, but the difference, we have different physics perhaps on different scales in different applications. And what we see here is a ski camber profile. So this is the profile of a ski loaded in a ski camber analysis machine. But of course, to see the height change, the height variation, I need to amplify it 100 times here. And we see the plantar pressure distribution of the skier and the equivalent loading position that is actually causing this camber profile. And that causes the glide zones to appear exactly where they are. And of course, it's in those glide zones that the friction develops. But then the multi-scale, and we will see what happens on the different scales. But you realize that if we look at the glide zones with higher and higher magnification, we will see different things. And all these contributes to friction in different ways. We will go into that more in detail here. So if we look at the loading condition, we have here positioned the skier in the tucking gliding position, G7, gear 7 sometimes called. And if the skier leans backward, I mean, typically more of the pressure is on the heels of the skier, and the equivalent loading position is further back on the ski. Neutral, well, like it says, sort of in the middle, and then forward leaning. And these positions, of course, affects how the ski camber distributes the load. And if we take the next slide here, we can see now how, well, schematically at least, how the load from the plantar pressure load on the skis actually causes load between the ski and the snow track. And also, if we exaggerate the ski cambers, we can see that their profiles of the left and the right ski will be different. I mean, this is now a dynamic problem also. Think of when you are gliding, I mean, there are always something that makes you not stand exactly with the same weight on each boot. So either it can be the track or it can be you that causes this. The resistive forces then here that results in the friction is mainly due to snow compaction. So if we glide in a like if we are skating, then we are constantly paving our way on the track. I mean, the track is prepared, but we are still doing a lot of snow compaction with the ski. And we will have some macroscopical plowing of the snow, perhaps if it's too grainy or if it's fresh snow falling. We will have viscoelastic losses both in the ski and in the snow itself. So there are quite a lot of things happening here on the macro scale. And that was for the ski part. So if we look more into this, we have the ski camber geometry. What is actually affecting this now? What is thought of affecting this? If we view the glide zones as two bearings in tribological, from a tribological perspective, we realize that these angles might be very important. First of all, the leading edge angles, and then perhaps the trailing edge angles, and if there are internal pockets and so on. And ski stiffness and damping, how the ski is built. Here we can see a broken ski, and we can see some of its interior. It has this honeycomb structure. It's a composite with a honeycomb structure, and it's also this particular ski also have wood beams or whatever you call them when they are that thin. But there are many different materials inside the ski, and that causes, of course, it to behave in a certain way mechanically. So again, we will have these losses as I listed. And now this ski camber, we can measure it, appreciate it, estimate it in different ways. And the traditional way is to place it in this machine. This is a ski selector, the brand, and then you place it in the machine and apply the load at a certain position with this type of shoe or whatever you can call this piece of load transferring interface to the ski. But what we quickly did here in Luleå is that we developed a measurement boot, because we understood quite quickly that this one will not distribute the load the same way as the ski boot does. And that can be quite clearly seen if we compare what we have a conventional ski camber measurement with the LTO boot measurements. They are rather different. So, and here is some illustration of this, how the load is affecting the ski. I mean, here it can only affect that area, but here it will affect a much larger area that will cause the ski to collapse in a different way. If we complement now this, now we come to the dear child of mine. So how to complement these measurements with some computational tribology. So we use our boundary element code and include both not only the load balance but also the moment balance of the ski. And we actually use an ANN which we train on the ski so that it can give us very quickly the ski camber for almost any load and position very accurately. So we can really we can run like quasi-stationary gliding in our tool here, in our numerical tool. Well, anyway, we take this tool, we take this contact mechanics software, and in that we make contact with the numerical ski and numerical stone. Because in the ski selector we have a stone which the ski is laid on top of, which is very flat. It is made very, very flat, so it's we can accurately measure the ski camber profile. Anyway, we put the ski in contact with a stone. We understand, tribologists understand that the contact here will be very small, even though we are on macro scale. And here we have a skating ski. So a skating ski is where you do same type of action as in skating. And a classic ski is where you go in these parallel tracks, and they behave very differently mechanically, because the classic ski needs to collapse in some way to give contact between the interior camber here, which is filled with grip wax, and the snow. So it collapses, you see, with half weight, ski is half body weight, it collapses much more here, even though we are on a gliding position. And if we move this position a little bit forward, it will collapse completely, like a digressive spring. Now, what the beauty with this is, when we have this model, and this model replicates very well what we see in measurements, then we can replace this numerical stone with numerical snow. And that will, of course, distribute the load in a completely different way. And now we are getting a little bit closer to what happens when we are gliding on our skis in a snow track or on a snow track. And here is the skating ski again, but then under both half and full body weight. I mean, half body weight would be when we were gliding just straight forward, standing with each much of the weight on both skis. Full body weight would be if we were gliding on one ski, and when we are skating, we are gliding on one ski most of the time. I mean, we do the technique in this way that we glide on either one of the skis. And the good skiers, they produce more than a body weight on the ski, of course, because they are jumping more or less up and down on the skis. But anyway, so that distributes the load quite differently, and of course that leads to compaction of the snow, viscoelastic losses, etc., which can be appreciated in some way, and hopefully we can correlate that with measurements and see what the friction is. Okay, so the ski is the upper part of the system. The lower part of the system also contributes, of course. And then on the large scale, on the macro scale, we have the ski tracks convexity and concavity. And I mean, if you here, I put quite high convexity and concavity, but you can imagine at least that the ski will behave very differently when you go in the concave region and the convex region, especially if you have grip wax in that span. Remember, as always, I mean, this is highly exaggerated. You can see the actual height here. Here is 1 millimeter. So 1 millimeter is here. So it's a very, very shallow hole there. And that can easily be filled with a little bit of convexity. And that would cause completely different situation in terms of frictional behavior, of course. And then also the properties of the snow, macroscopically, stiffness and hardness. What are they? So these are contributing to resistive forces here. The ski track, the ski track geometry or profile, and that one we can map with very high accuracy with a GPS, and with a highly accurate GPS, namely a real-time kinematic global navigation satellite. What is it? Global navigation satellite system, I guess. So if we use that, we can have an accuracy in all three directions of around 1 centimeter. So for this rover module, we have just let it slip down this descent, and we can capture its position with very high accuracy, and we can also therefore capture its speed very accurately. We cannot measure the friction directly. That we cannot, never do. The friction, that one we must somehow calculate. The friction coefficient we must calculate. But based on this measurement, we can. And we will see how we can use these measurements to actually receive both the friction coefficient during acceleration and during deceleration. And these can be completely different. Which is quite interesting. Now on the mesoscale, we have these glide zones. That's the size of the mesoscale. And of course, they will be out of flat. And there will be pressure zones or pressure points. which the ski actually glides on. Perhaps we will have pockets, and well, these angles we were talking about before, they will contribute. And we will also have some torsion of the ski, and therefore we cause edge effects, and they can be rather large. But we understand now, if we have these pressure zones or points, if they are located at the place where we have most of the macro scale pressure developing, then this one will plow the snow much more than if they are on another location. So the location of this is very crucial, and this is really hard to appreciate, to estimate, measure. But this is why two pair of skis, for example, made just after each other in the same machine, they will not have the same glide performance. There can be quite substantial differences actually, because of these small factors. And then coming down at the micro scale, of course we have the topography of the ski base, and now the gliding direction. Can you see my pointer, by the way? Good. So the gliding direction is this way, and here we have 2 millimeters of texture. Well, as long as this one, between two of the deep ridge, or the deep grooves here produced by a hand drilling machine or hand drill. So we can measure this. We can also view it with microscopes of different types, and then we see different things, of course. So with polarized light, we can see the grains and how they are connected to each other. So these are the grains of the polyethylene in the material. And now microscopical plowing is the contributor to resistive forces. And of course, the rougher the ski base, the more plowing. But on the other hand, the rougher the ski base, the less wetted part of the contact. And therefore, it may reduce the friction in this respect. To produce that structure of the ski, we typically use a stone grinding machine. And these are quite sophisticated nowadays, and they even allow for computer programming, but they also typically have these interfaces, programming menu, where you can set a number of parameters. For example, you can set the speed of the stone. But to produce the texture, the structure of the ski, you must first structure the stone. And you structure the stone with a patterning tool. So it's just a diamond tip, which you can then control. You can control the depth that is pushed into the stone, and then you can control the speed of this one as it slides over the stone surface. And in combination, and that you can do from side to side, and then you can do the grinding in a sequential manner. So you have several grinding processes finally ending up in the finished one. But if you have a certain speed, a certain feeder speed on that diamond tip, it will produce a certain pattern on the stone if the stone is spinning in one speed and another one in another speed. And that it depends on many things, of course, because the stone here is a porous material which has been pressed together. So you're gonna pick out pieces of that stone with that diamond in a stochastic way. Then when you grind it, you need the feeder wheel, which is pressurizing the ski onto the grinding stone. and it also moves it through the grinder. This gives the structure, and you can program many parts of it, as I say. So it's almost too many parameters for us to handle, but it's fun. We have all these degrees of freedoms. Now the grind, I mean, even if the elite athlete has 30 pair of skis in their garage, the grind cannot be too specific. So for an actual condition, they need a certain topping, they need waxing, and they need an extra pinch of texturing, typically done by rilling. I don't know, we call in Swedish, we say rilling, we rill the ski. I don't know if this is exact English translation, but I mean, we take this tool and we press it onto the ski base and glide, roll, or slide it over it to create an additional pattern. And here you can see, for example, this tool has created these deep grooves on the stone ground and waxed and brushed, scraped and brushed surface to reduce viscous friction, to reduce capillary drag. On the other side, we have the snow, of course, and that deforms. And here's some 3D tomography of this by other researchers. Now this was supposed to be moving, I guess, but it wasn't. This was supposed to show different. It's an animation of how the snow is displaced when you are moving over it, and it was actually looking very nicely before I showed you this. It has stopped moving. With that, and here it has also stopped. Now I cannot access this one either. This was supposed to be a movie where we went into the material, but anyway, that you can perhaps depict, that we can move into the material and we can see both the grain structure and if there are other constituents within that one. In tribology, we have lubrication. Tribology is friction, wear, and lubrication. And the lubrication here is partly produced within the contact by friction. So friction melting causes some extra lubricant, water, to glide on. And I mean, these are just very, very thin films of water, and perhaps it's not really water, it's a quasi-liquid-like layer. And it's important that the water is not all over the place, but it's located at the contact spots, which altogether mounts up to a small area. Because then we can have low friction. Too much, we will break too many bridges, and if we have even more, I mean, the capillary forces associated with thin water films, they are tough. It's a tough one to break. How to deal with this? Yeah, we have been talking about a lot of that, and that is texturing. So the surface texture itself, both the stone grind and the additional one, and the wax, of course, to improve it even more. So how to quantify the ski friction then? Many ways of doing this, typically and very practically done in pair glide tests. So you can do a knockout contest, and quite quickly you get a winner pair of skis. You can do time trials with skiers, that's also quick. Be sure that you have a good design of experiments and a feasible number of tests, and hopefully you can get an average minimum time which actually decides the best pair of skis in this case. I mean, and what we could test the structure, ski-based structure, and or wax, for example. If you take away the skier, the human factor is no longer there, and that can be quite good. I think it has disadvantages too, of course. And here is one example where we did this glide test. So we measured the time it took for the sled to run 30 meters. And we can all see that the first test in each set here is the fastest one. So we let it slide down, we pulled it back, let it slide down again, repeated that 5 times here. Again, 5 times with a new pair of skis, new pair of skis, new pair of skis, new pair of skis. And you can see that the glide time increased every time, but also the glide time reduced during the tests. So the way was paved, the track was getting better and better frictionally. And yeah, so there are many aspects we need to think of when we test the glide performance of skis to reduce the friction. Now remember this unmanned test with the RTK GNSS, then we can get the velocity and also the height profile of the track. And if we feed that into some numerics built on Newton's second law only and run some optimization, we can obtain friction coefficient. And here is a display of that, and we can see that the acceleration, average acceleration friction coefficient is twice as high as the retardation friction coefficient. And this is quite interesting. And we can talk a lot about the reasons why this is. Now, if we do this a lot, I mean, we can see very clearly, and we can compare different pairs of skis in terms of acceleration friction, deceleration friction, and top speed. And in this test, there is a yoker pair of skis. So there are 6 pairs plus 1 more, and the yoker, it actually sits here, and we can discern that this is a race waxed pair of skis which has significantly better top speed, lower deceleration and low deceleration friction. So it's quite interesting. That is outside. Outside, there are many factors affecting the friction which we do not have control of. So if possible, it's good to be indoors, and there are many examples of indoor facilities for doing glide tests. This one is a huge one where we actually can run our sleigh if we equip it with a measurement method that can be used indoors. And we have that now. So we have a non-contact optical sensor which we can capture the speed with very high accuracy. And that means that we can obtain the deceleration friction coefficient from numerics, running it through the Newton's second law. Because even though this is just a small guy, he will still have air drag. So we have to remove that at least from the deceleration data, the speed data, to deduce the deceleration coefficient of friction. I don't know, was that one? That was supposed to be an animation. I can quickly show you. So we start this thing up with a winch. There was some cushioning material loosening from the winch, no problem. But in this way we can do very controlled experiments indoors, and and get quite accurate estimates of friction for different skis structured in certain way and waxed in certain ways and so on. And now with that, with all these methods, what I've showed you, that our work continues towards our long-term goal, which is to start with 2026, for Milano Cortina Winter Olympics. And here, of course, we need to do the optimism. We need to include the athlete. So, I mean, taking a certain athlete and giving them a certain pair of skis will produce one gliding resistance. Another athlete on the same pair will have another resistance. So we need to combine the athlete, the ski, and the structure and the waxing all together to optimize for the skier. And this also includes, on this picture, it doesn't show the track. But of course, the topography of the ski track is also affecting this, because this certain athlete will perform differently in different parts of the ski track. And then you can optimize the resistive forces, or optimize for the resistive forces in that respect too, or should. With that said, I would like to conclude this presentation, and I would like to thank the sources for funding that we have, and I would like to thank you for listening in on this webinar, and I hope to receive some questions. I hope I didn't go too long so that everybody fall asleep.
It is very interesting.
I have some questions. Yeah.
Thank you so much for the presentation, and I would request everyone, if there's any question, please, you can unmute yourself and ask. And I think we will keep this discussion for just 10 minutes to stick to the time frame. Anyone? If you have any questions, please ask.
If I may, please. Yes.
Yes.
Well, thank you very much, Andreas, for this interesting presentation. And my question pertains to the properties of the snow. And I was wondering, because, you know, it may have some very difficult to assess rheological properties, and it depends on the conditions, and then the outside conditions, and the wind and the temperature. And I was wondering if you looked into that, how have you considered the properties of the snow and the relationship between the type of ski that needs to be used versus the type of snow? Because obviously we have no control over the snow conditions, but what we can control is rather the ski type that we can use for a given type of snow.
Absolutely. And there we have, there we have to our help all the empirical knowledge that the national team, the waxing technicians in the national teams have gathered all those years. So they know, for example, that this type of ski is really good for this condition. Okay? They know that it is sort of optimal, but what they don't exactly know is how to combine now the ski to cut that last percent of friction. You know, you really need to combine that ski with the right structure on it and the right wax and so on. And there comes it is there we are trying to help the national teams. You know, but the questions you are posing, these are really things that you have to struggle with when you are doing ski tribology. So it is very difficult, because even if the snow indoors in our indoor arena in the next the neighbor town here, Piteå, if all the conditions are the same, and you let the snow sit there for one day, it has changed. it constantly goes through this metamorphosis. So even if we have artificially produced man-made snow, which is very controlled, and we can repeatedly do this over and over again, it will constantly evolve. But the good thing with being indoors, at least, is that we know that, and we can go there exactly when the snow has been laying there for 24 hours after production. And then we have very similar conditions, at least, and therefore we can really test out things. The drawback is, of course, that indoor arena, it doesn't really represent the reality on the ski track, and then we have other conditions. So what we are trying to learn, I mean, that are the mechanisms. So when we look at the data that we get from our measurements, we are really trying to discern, in which phases, regions, what type of mechanisms are actually the main contributors, and how can we find a remedy to remove the problems caused by that mechanism. So that's how we work. And
okay, thank you. Well, I guess I tried to jump to the end conclusion of this, while probably you're still at the initial phase of investigating what's happening. So, but yeah. Anyway, I guess the final goal is there. You want to, in the end, improve the performance and get better skiing performance for the athletes based on the conditions at hand, which you have no control of.
But I mean, in the meanwhile, we are playing with these type of things, and we are learning how the ski mechanics actually distributes the load on snow, and how that affects the contact mechanics. I mean, we are here doing quite a lot of very interesting things to me.
Yes, I can imagine, of course.
But to the waxing teams, I mean, for them, they would really, and the Swedish Olympic Committee, they want the medals. They want podium positions.
You still have 4 years to work on that before the next Olympics.
Yeah.
Good luck. Thank you, Andreas.
Thank you, Wasim.
Thank you. I think we might have one more quick question.
Yeah, if I may.
Yes.
I mean, going back to contact mechanics, in the end, it's the part that I really enjoy. And you said, and that's obviously true, that the contact mechanics conditions are quite dynamic in nature, even, just vibrations, even if you try to be exactly still, will be quite important. So have you done any attempt on kind of modeling these dynamics and seeing how, because even, I don't know, even if the position of the contact or the loads and everything, how they change, is there an estimation how big this can be?
Well, not really. I don't think we have done what you are after exactly, but what we have done is, for example, I mean, we have studied this, how the glide zones moves and evolves, how the real contact area evolves when you are subjecting the ski to dynamic loading. I mean, during let's see here, now this is sort of quasi-stationary experiment, so you can stand in a gliding position, hopefully you're not jumping too much up and down, but you can be there quite steady. And then you get this picture. But imagine if you just do a polling cycle and you do that over and over again. We have studied this, and then we can bring that polling cycle into our contact mechanics software, and then we can see how the glide zone distributes the load. We can also see how the ski camber collapses. And then we can determine, for example, how much kick wax can we allow for a certain skier without without reducing the glide too much. You know.
Yeah, that was actually a bit what I was after, this thing that if you don't know exactly where it glides, then you cannot really apply the treatment on the right spot. So
yes,
but then again, that's already quite a complicated topic, is to find where to apply the treatment, let alone what treatment to apply. So, but very nice.
Yes. So sorry to interrupt. I think we have to end this seminar now because we only have 2 minutes left for this. And I thank Professor Andreas so much that for delivering this wonderful presentation on this beautiful topic. I hope everyone were very enthusiastic to know more about this. And also, if I also want to suggest everyone that if you want to take part in discussions regarding this kind of topics, I think we TriboNet, we have already introduced a platform called Tribo Network, where we are trying to connect all the tribology community at one place. So I think that would be a best platform for everyone to explore and take part in the discussions there. So please do take part. And I thank Professor Andreas again to accept the invitation. Yeah, thank you, Professor. And I also thank everyone for attending this seminar. Thank you all. And until next.
Thank you.
Yeah.
Thank you.
Thanks to you.
Thank you. Bye.
Have a great day. Thank you, Andreas. See you around.
See you.
Thank you. Bye-bye.
Thank you. Goodbye.